Okay, hi again, and continuing with our fundamental theorem of calculus, let's now look at number 29 on page 99 of the MAT1512 study guide. And in that example, we are given capital F of x is equal to the integral of 3 to x cubed of sine cubed t dt. Alright, and what we are asked to do is to find the derivative of capital F of x. Alright, so a dead giveaway that you should be looking at the application of the fundamental theorem of calculus is that this is quite a difficult integral to evaluate. But the fundamental theorem of calculus comes to our rescue by saying that we can easily evaluate this by just replacing the t's with the upper limit of the integral. Right, in this case it's simple because we have a constant as our lower limit of integration and we have the function as our upper limit of integration, so we don't need to change anything here. So f prime of x would simply be equal to sine cubed of x cubed. But since we saw in the previous example, what we're actually doing is in the steps in between is that we are taking the derivative. So what we've got to do is we've got to apply the chain rule and take the derivative of this function with respect to x, which gives us 3x squared. So the final answer for this one would be, if we just write it a little bit neater, 3x squared sine cubed of x cubed. And that's it. Alright, hi again. And now we're still on page 99 of the MAT1512 study guide. And this time we're going to look at the last example in this series, which is number 30. And here we are given the function f of x, and that's capital F. And the capital F of x denotes that it is a function which is an integral. And this is quite a difficult function to integrate, which gives us the immediate indication that we will probably have to apply the fundamental theorem of calculus to this problem to be able to solve it. And applying the fundamental theorem of calculus to find f prime of x, all we need to do is we need to substitute the x, or the function of x, in for the t, and that then gives us the 1 minus sine squared of x, and because there's a differentiation step hidden inside here, we've got to apply the chain rule by just taking the derivative of the sine x, and the derivative of sine x is cos of x. Right, and that's it. We can simplify this a little bit by doing a couple of tricks. First of all, from a trig identity, this equation here, or this, what's inside the square root, is actually equal to cos squared of x, and the outside here is still cos of x, and that then would simplify to the absolute value of cos of x times by the cos of x, and there's the answer. Now you're probably wondering, how did I go, or why did I go from this to this? How did this square root of cos x become the absolute value of cos x? And to explain that, we can look at the trig graphs. So starting off with the graph for cos of x, and this we know looks something like that, and we go from 1 to minus 1. Right? Now, if we do the graph for cos squared of x, then we would still start, plus 1, we would still start at 1 because 1 squared is 1, and we would come down to the point where it hits 0. But at that point now, the cos graph goes negative, but when we square it, it becomes positive. So essentially it flips up to the top like that until we hit this other 0 point, in which it just continues on its previous path. So that is what cos squared of x looks like. Now, if we take the square root of cos squared of x, then we just basically go, we still square root of 1 is still 1, and it comes down, and the square root of this doesn't change anything, so that is what that would look like, and that is essentially equal to the absolute value of cos of x. So you can see that this graph is the same as that graph, where the negative side is inflected to the top. So what I mean is, this is inflected or flipped up vertically, and that is essentially where this absolute value comes from.